If you've got asthma or you know someone who does, there's a real chance one specific letter of DNA on chromosome 17 played a part in that. And that same letter is quietly linked to type 1 diabetes and a couple of other autoimmune diseases most people have never connected to asthma at all. So it's one switch, but several completely unrelated diseases. And that's the kind of result that makes geneticists sit up. So let's go sit that hidden in real biobank data and then figure out what's actually doing. Okay, same map as always. Unlike the previous video, this isn't about one population carrying a rare variant. So this variant is actually very common. It's found across most ancestries, and that's exactly why we can hop between a few different pins here and watch it show up for completely different diagnoses each time. Let's start with FinGen again. Let's look at the signal here. Okay, so look at the top of the list. Asthma absolutely dominates the top here. And this is a well replicated finding. It was actually the original signal that put this whole region on the map back in 2007. And it's been confirmed since in cohorts, across Europe, Costa Rica, and East Asia. Now, here's where it gets interesting. So let's go back to the same variant somewhere else. Let's go to Japan. And okay, different biobank, different population, same variant. And look, there it is again, except this time it's not asthma at the top, it's allergies and autoimmune diseases. Nothing to do with airways at all. And that's not a coincidence. It's the reason this locus has been studied so heavily. So whatever this piece of DNA is doing doing it to something that matters across a huge range of immune and inflammatory conditions. But before we move on with the video, I want to say a quick clarification. So carrying this variant doesn't mean you'll get any of these diseases. It's a common variant. Plenty of healthy people, probably including you watching this, carry it. And all it does, it shifts risk rather than deciding an outcome. So what makes this whole thing worth an entire video isn't that it's a dangerous, mutation on its own. It's that one piece of non-coding DNA can nudge the odds on these many different diseases at once. Okay, so here's why one switch can cause many different diseases, as we just saw. The variant sits in the middle of a cluster of genes. So we have ZPBP2, GSDMB, ORMDL3, and IKZF3, which are all lined up right next to each other on chromosome 17. This one, ORMDL3, is involved in a lipid synthesis pathway that affects immune cell function. GSDMB is part of a family of proteins involved in a form of programmed cell death called pyroptosis. And IKZF3 is a transcription factor, which is very important in B cell development. So we have three genes with three very different jobs, all sitting close enough together that one regulatory element could plausibly affect more than one of them at once. And that's exactly what researchers found in this paper, which is like the basis and the foundation of this entire video. So the risk version of this haplotype pushes GSDMB and ORMDL3 expression up, while it actually pushes the neighboring ZPBP2 gene down. So one switch, three genes, and moving in different directions, right? Now, how does one piece of non-coding DNA manage to turn some genes up and another down? And all of this is happening at the same time. How is that possible? And that comes down to a protein whose entire job is holding chromatin architecture in place. Okay, so this is CTCF. If OCT4 was the protein from last episode that grips a specific short sequence, CTCF is almost the master version of that idea. It's one of the most important architectural proteins in the entire genome. So look at this shape. This isn't one folded domain, it's a whole row of them. And here's another view of the same 3D shape that really shows this idea. So this is the same protein. Now we're looking at the protein domains. And these blocks that you see, these are zinc fingers. And we have 11 of them in a line. And each one grips a different few letters of DNA. So they are strung together, and they let CTCF read a fairly long, specific sequence and clamp onto it with real precision. And here's what CTCF actually does in the cell. DNA is organized into loops, and CTCF is one of the main proteins that anchors those loops in place. So where CTCF sits, it can act like an insulator, a boundary that keeps an enhancer in one loop from reaching over and switching on a gene that's technically nearby, but supposed to be in a separate regulatory neighborhood. Let me actually show you that instead of just describing it. So this is a model of exactly that boundary. We have two CTCF anchors holding a loop shut around one gene. And right now we're looking at the normal DNA sequence, and CTCF's grip is solid. The boundary is doing its job, right? The enhancer's activity stays contained on this side. Now, watch what happens when we insert the mutation. So if you have this version of this variant, this is what's going to happen. The anchor loses its grip and the loop opens up all of a sudden, and the enhancer's reach extends past where it used to stop. So, that's not a metaphor. That's like the actual shape of the mechanism. A boundary that used to hold now doesn't. And here's why that one broken boundary explains 5 different diseases at once. It's not that this SNP touches 5 separate disease pathways directly. It's that it touches one chromatin boundary, and that boundary happens to sit right next to a cluster of genes that I just showed you. And each of these genes is involved in a different immune or inflammatory condition. So you weaken the boundary once, and every gene sitting near it gets affected at the same time. Some are pushed up and some are pushed down, depending on which side of the old boundary they were sitting on. So next time a GWAS hit looks messy, showing up for a bunch of seemingly unrelated conditions, don't assume it's a coincidence or bad data. Sometimes it means you found a structural piece of the genome, something that's holding a whole boundary in place for a cluster of genes, not just one. And yeah, if you want to play with this tool I made for this video, let me know in the comments and I'll share it with you. Otherwise, that's it for this video, and I'll see you in the next one.